Alright, so let's start with rotational motion. And perhaps the first thing that we should do is to define what a rotational motion is. So first let's talk about what a rotational motion is. And in a purely rotational motion, we have all points on one object move in circles around the axis of rotation. So think of this as a simple disk. So every point of this disk, regardless where it is rotating around this axis, and that's why we kind of refer to it as rotational motion. Often, it is very practical to set kind of new quantities to describe this motion. You could use for a single point kind of circular motion type of formulas, but soon you will find out that there is a certain practicality in describing angular quantities of this motion. And so think about it, that typically what we would say is, well, in kinematics, how far is this point traveling in a given time as it rotates? And we could express this as a length of this arc, but maybe instead of saying, well, how many meters is it along this arc, we could say, well, what is the angle that it travels in a given time? And therefore, we could define angular displacement. And then, therefore, if we're going to have angular displacement, we can also define angular velocity and angular acceleration, right? So it's kind of describing the motion, but looking at it from perspective of an angle. The reason why these angular quantities are useful is that if I think of, for example, this point P, and let's say I would select another point that is closer to the axis, what they have in common is that they travel the same angle. They do not travel the same length. Obviously, point P will travel longer distance than maybe a point that is closer to that axis. And that's why these angular quantities are somewhat helpful in describing this motion. So here, if we want to define the angle that is traveled, well, that would be defined by length of this arc divided by radius, or the distance from that rotational center. I'm sure you've seen this formula in math when you were doing probably sine, cosines, and some of those functions. Okay, so let's talk about then angular displacement, angular velocity, and instantaneous angular velocity as quantities that can be perhaps quite helpful in describing this motion. So angular displacement. So how do I define angular displacement? Remember, how did we define any displacement in kinematics? We said final position minus initial position. So here, the angular displacement will be whatever is the final angle that the object travels minus the position at the beginning. So from this point to here would be angular displacement of the point that is perhaps rotating, right? So it's the kind of same idea as in kinematics, change in position. Here it's the change in the initial and final angle that is traveled. And then that gets us to angular velocity. Well, again, in kinematics, how did we define velocity? We said, well, it's a change in, or it's the displacement over time, how long it took to make this, to travel this displacement. Well, we're going to define angular velocity. It's going to have symbol omega, average velocity. I'm sorry, the slide is a little bit off here. And that's going to be defined as change in the displacement over change in time. Now, this formula you don't have to really worry about. That would be the definition for instantaneous angular velocity, right? And you would be getting into a calculus, right? So again, angular displacement is change in angular position of that point, and average angular velocity is change in the angular displacement over time it took take this change. And again, going further, we can go to angular acceleration. So again, how did we define acceleration in linear motion? Well, we said it's the change in velocity. So in this case, change in angular velocity over time it took. Again, any of these formulas with limits, you don't have to worry about it. Again, they would refer to any instantaneous velocity, but you'll be mostly dealing with the average values, because we will be dealing with a constant motion, meaning it's not going to be a non-constant acceleration, right? So we have three quantities. Now, the other thing that we need to kind of think about is the fact, how do we relate? Because you can think of it, whenever something is rotating, it has its kind of linear component, and it has also this angular component. Just think about the ball rolling. Well, you could look at every point and you could look at it and you could say, well, how is it kind of rotating as a part of that rotational motion? But at the same time, that ball is rolling perhaps forward. And so the question is, how fast is it moving forward? And certainly, the higher the frequency of that rotation, well, you're going to probably perceive it rolling faster in that linear motion. And so it's always important to remember that the relationship between velocity, linear velocity, and the angular velocity is such that v equals r times omega. So if I know the radius of this point, right, how far is it from that center, and I know that angular velocity, I can figure out how fast is it moving, or what is its linear velocity. And this would be measured in meters per second. This one is measured in radians per second, and radius would be measured in meters. Right? So there is a relationship between that linear part and the rotational part. So this is extremely important because this brings us to this idea. So imagine you're sitting on this disk, and certainly the point that is closer, right, will have probably different linear speed than the point that is further away. And why is that again? Because this angular velocity is same for both of those points, right? They have to have the same angular velocity, and therefore if this radius is different, that means linear speed has to be different. And it makes sense that further away you go faster. Why? Because you have to travel kind of a longer distance over the same period of time. So the linear speed for the objects that are further away from the rotational axis is essentially greater. Very, very important here for kinematics. Now, another formula that we need to look at is the acceleration. So we know that any point that is rotating, it's kind of like in a circular motion. So we have that radial acceleration, which is v squared over r, same as circular motion, and then the tangent to that is tangential acceleration, and that acceleration is again r times alpha. So this is angular acceleration, and this is kind of that linear aspect of it, right? So again, same relationship between linear and the rotational acceleration. And this formula just puts 2 and 2 formulas together. So if I plug in for the velocity r times omega, I'll get this relationship. And this is going to kind of get us nicely to that relationship between displacement, velocity, and acceleration. So what we did up until now is kind of that x, v, and a, which is displacement, velocity, and acceleration. In rotational quantities, when we use angular quantities, we have angular displacement, angular velocity, angular acceleration. Right? Angular, this is measured in radians. Angular velocity will be measured in radians per second, and angular acceleration will be measured in radians per second squared. And these formulas link the rotational and linear aspect of any point that is in that rotational motion. And I believe that these formulas are in your formula sheet. Okay. This is just a review of what you know, and what you know is what is frequency and what is period. These are still relevant quantities, as they may describe often. You may be given how many rotations per second or time of one rotation. So you know that you can always transfer between those quantities. All right. And this is really important aspect of transferring between these two quantities. So for example, angular quantities, and look at the similarities, and linear, right? So everything works exactly the same. So final velocity of an object is initial plus acceleration times time. Final angular velocity is initial plus angular acceleration times time. So you just interexchange the angular quantities for linear, and the kinematics formulas work exactly the same way. And what I'm going to just mention here is rolling motion without slipping. So if you have such wheel that is traveling and rotating, so you could look at each of these points and describe the rotational aspect of it. But I think what is important to understand is that if you were looking at that wheel as a whole, and you're looking at, well, how fast is it moving, as if I were looking at it in that linear motion, then that speed is expressed as r times omega, which is omega is angular velocity, r is the radius of that wheel. So you can always find that linear aspect of how fast is something moving. And this is really just the key basic of the kinematics of rotational motion.